Now, like I said earlier, you have all these, different parameters, different choices, and as you can see, these choices aren't necessarily, learned by the network itself, right? Because in order to start learning the network, you need to have already made these choices. So you cannot consider learning these choices as a part of the learning process. And therefore there is this idea that what if these choices could also be learned, right? There is a learning process, and in order to do the learning process, you need to have these choices. What if there is a learning process for the choices? So in some way, you can think of this as like a meta learning, that is learning over the things that you want to, that will determine your learning process itself. And again, if it is, like a little too confusing a word, don't worry. The idea is, can we optimize these hyperparameters, these choices also? And one of the and there are several algorithms that have been proposed. Obviously, one choice which most people do, and is an expensive process, but is very straightforward, is why don't you just run your network with all these different choices and pick the one which has the best result. So in order to do that, you need to have a separate validation set, and then you can optimize over this validation set. So, but the problem is, you can see this. These are only few of the choices. There are so many other things that will impact. This is too expensive a process, and therefore people have designed more sophisticated algorithms which will do this. Now, as far as this course goes, all the assignment goes, in general, for 90% of your deep learning work, even in the industry scale, you don't need this, because these kind of techniques, they are good on an academic level where you can show they're really useful, but in practice, and again, I've been practicing deep learning for a long time, where there are a lot of hesitations in using these things in a real industrial setup. But it is good to learn about these things, so that if there's a situation that arises where it is a good idea to apply this, you should definitely not hesitate from applying this. Now, I'll just give you a brief of one of these algorithms, and again, this is a little too complicated for an introductory course, but I encourage you to read this paper. It's well written. Definitely, it's very heavy in the details and the math. But if you towards the end of the course, probably you will have all the necessary knowledge to understand this paper. So this paper is called as a model agnostic meta learning. Most people refer to this as MAML, MAML. Here, the idea is basically this, right? So assume you have set number of things you want to do, right? Here, set number of things could be basically all the different choices that you have to make. What type of learning rate, or what type of optimizer to choose. So all these tasks, the task doesn't necessarily mean different problems, although in some setting it could be that you have the same network, same model, and you have like different data sets, and you want to basically make a model that works over all these data sets. So in that case, the different data sets would be different tasks. But in this case, we have one data set, but all these choices over network. So those different set of networks are your different tasks. But what if it is, we have set of tasks? So let's call them the distribution of tasks, that is P of tau. And now let's assume you have these two parameters, alpha and beta, right? These are step size. The way you had learning rate, similarly you had now learning rate for the meta learning, and they have two learning rates, alpha and beta. Again, you start like a standard process where you initialize your network with random weights. Now you sample a set of tasks, and then for all of these tasks, you do your learning process, your SGD, as we have discussed. You evaluate the gradient of the loss, for k examples. And here the idea is, you don't want to do this over all examples, because that'll be too expensive, but you need to do for sufficient number of examples. You update the weights using your update rule, which is your stochastic gradient descent. And once you have done this, now you update the parameters again, but now you use the gradient over the set of tasks, and you need to be able to store the gradient as you compute this. So as you can see, basically this is applying SGD over the whole network itself. That is, you are storing the gradient of all of this. And again, I'm intentionally not really getting into the details of this because the actual implementation of this is a little bit complicated. But think of it as doing two-step process where first you're optimizing for a certain for specific tasks, then you are optimizing over a set of tasks. And in order to do that, again, you are now computing, you're accumulating gradients over a set of tasks. And once you do this, you just keep repeating this for a certain number of steps. And you can see there's two learning rate. One is internal learning rate for each individual task, and one is outer learning rate for all the set of tasks that you do. And this is really useful when when you have a lot of different tasks, and it will be computationally infeasible to basically separately optimize the network for each of the tasks. And okay, just to give you an highlight of like how well it does. So you can imagine here that you have this different benchmark, different data sets, and this mammal, which is this network, and without any convolution layer, does 89.7, whereas the baseline numbers are much smaller, like the 82.8. These are just your accuracy. And again, some of these data sets you might not be familiar with. We'll definitely learn more about them in the future classes, but just to give you an idea how well the mammal does compared to like fine-tuning baseline means you're taking a network, optimizing it one at a time. You don't do so well, but if you do this mammal, you optimize over all the parameters, all the tasks, you do significantly better. Okay, now let's switch gear and let's talk a little bit about regularization. I think we did discuss a little bit in the previous lecture, but especially for deep learning is very important because we have a lot of different parameters, right? And now question is, as you can see that the more degree of freedom you have, more likely that you will learn some function that really has very low training error, right? Because like this yellow line is your model, right? It passes through all the training data, all the training data points, and it's important. Problem is, if the true function that generated the data is the pink, but if what you're learning is yellow, it's not going to generalize well, because beyond this point, all the beyond this edge, all the points that this pink line generates may not generalize over this yellow, because there's no reason to believe that this yellow will hug the orange curve after this point. This is a classic toy example about overfitting, but this is very, very strong possibility, especially in deep learning, because we start with a lot of different parameters. So in order to do that, in order to prevent weights really overfitting, one of the most common techniques of regularization is to decay is to regularize the weights. That is it's also called as weight decay. That is, you penalize the weights if it is too big. That is, and like I said, this goes back to the idea of your starting weights, right? You initialize your weights to be close to zero. That is, initially you say that these weights are close to zero, but they are they don't do anything. They don't do anything useful. They are not trained. But then as you start to optimize, the weights will start to move away from zero. So as they grow, as the weights get bigger and bigger, they become more and more useful. But if they become too big, you penalize because you want to add an extra penalty for the weights to be too big, because that kind of prevents the model from overfitting, because the values that are really useful in the training might not always be useful in the test, right? That is why if the values are close to the training, it is it is another form of Occam's razor, where you're saying that simpler version, that is the one which requires least assumptions, is true. And here assumption just means the magnitude or the norm of the weights, right? And again, if this is confusing, you can just imagine that if you have smaller weights, you are less likely to have a function like this yellow line, and you are more likely to have a lower degree of freedom, because the expressive power of the network is very limited, and therefore this network is regularized. And it used to be very common to use regularization, but these days it is hit and miss. For certain type of task it really works, especially if you have dense layers. but for certain type of task it may also not work. So if you don't see any improvement by doing regularization, don't be surprised, because it really depends on the type of the network and the type of the task, right? So let's say your regularization is an L2 norm over weights. So here W means all of your weights, right? And basically sum of all your weights, and this is the square of all the weights, and this is square because whether weights are positive or negative, you want to penalize it for being too big. So we are only interested in the norm, not on the direction. Now here the total loss would basically be your actual loss, and then you have this regression term, and and like I said, your loss always needs to be differentiable, right? But as you can see here, this is easily differentiable because this is the square, and we are starting with this 2, so that when you take the gradient, this 2 and 2 cancels out, so basically you're left with alpha W. Now what is alpha? Alpha is again like a learning rate, or a step size for this weight, because we don't necessarily know what the norm value would be. So you want to basically use the alpha to control how much penalty do you want to add, because if you add more, if the value of the alpha is large, you are really penalizing the network for having big weights, but that might also suffer because now the network will rather have lower weights than have a lower loss, because we are optimizing some of this, right? So if this has a higher weight, the network will focus on this part, which will just try to keep the weights lower. But if the alpha is too small, then this will dominate, and this might not have the impact you need. And the only way to find alpha is again to do the hyperparameter tuning. That is, you just try a bunch of alphas, or if you are really into doing meta learning, this can be part of your meta learning parameters. And now the new weight, so now when you update your weights, the new weight is basically your this whole thing, that is alpha W that is your old weights plus the gradient of the weights and with respect to the loss. And again, there is this epsilon term, because now this epsilon is like the overall learning rate of this, but oftentimes people use alpha here, 1 minus alpha here, and not epsilon, in that we only have one parameter, and then you can control if alpha is lower, then this is closer to 1. If this is closer to 1, this is closer to 0 if you have 1 minus alpha. But again, I will encourage you to look into the implementation of this in Keras or also in the textbook, and that will make more sense. But definitely try to play with the different values of alpha and to see what kind of regulation you get. And the way to test whether you are able to regularize is your validation loss should be lower, because it means you have more generalization. That is, the network is overfitting to the training data less. That is, therefore, is generalizing to the test data or the validation data more. Okay. However, if you find this regularization too complicated or intricate, easiest form and the most useful form of regression is called as dropout, right? So let's say on the left, if this is your standard multilayer perceptron and all these arrows are your weights, during training randomly some of these weights are made into 0, or you don't use them while doing the forward pass, right? Just assume that they don't exist. So even though this whole thing is a network, in practice the actual network in the forward pass is some combination of this. But the idea is this combination changes in each different forward pass. That is, first time you do, it could be this combination, and next time you do this, maybe this weight comes back, but this goes away. So each time you are kind of learning different combination of neural network. So each weight might get different number of updates, because it depends on whether they are turned on or turned off. Now the question is, how do you decide what it is? For each of the weight, you just say, I will just flip a coin, and if the coin is heads, I will keep that weight, or if the coin is tails, I will not use that weight. So when I say not use the weights, you just literally assume the weights are 0, even though they are some other value. For that particular forward pass, these weights are 0. Now, what benefit do you get by doing that? The benefit you get is no weight is so dependable, because the network has to learn not to use that weight to do the task, and therefore you have less chance of overfitting, because all your features are distributed over the set of weights. And as you see, if each weight is turned on and off at a rate of 50%, by definition, at any point in time, this network is only learning half the weights. So this network has half the real parameters compared to this. So just by virtue of having less parameters, this will have less overfitting. Of course, you might ask the question, then why not start with a network that has actually half the number of neurons? But turns out this type of network where in reality there are more weights, but in practice it's only half, but it is combination of half of all the weights, right? So the features are really distributed over all of this, and it turns out that works a lot better than just starting with half the number of weights. And again, the paper for dropout, which unfortunately I think was rejected when it was originally submitted, but now is like one of the most cited papers in deep learning. It's very well written, and it's almost self-explanatory. So I would encourage you to read the paper, and feel free to ask questions if you have on the Slack channel or via email. Okay, let's look a little bit more into this, right? Because ultimately we also want to see how is this implemented. So at training time, right? So what you do is, for with any probability p, right? Each of these weights are either turned on or turned off, right? So now it means, the total weights, because if you remember the value e, right, the activation, that is input multiplied by input multiplied by weights, and then it's a sum of it, right? But now question is, if some of the weights are off, then the total value will be different, right? Because in this case, if half of them are off, the total value will be will be only sum of the weights multiplied by the input. So during test time, where you are going to use all the weights, and by the way, I forgot to say that, but in training time, yes, you are turning the random set of weights on and off, but during test time you're using all the weights. So that is where you have this power of distributed feature importance comes into play. And now, but the problem is, in the test time, if you're using all four of this versus in training time you're only using half of this, the total sum will be different, right? So that is why in test time you basically multiply it by p. So if let's say p was half, so the total weight should be half of this. But as you can see now, this means during test time you need to remember what the p was, which was used during training. This is not ideal. So in practice, what people do is, during training time, you basically multiply all the weights. So you divide all the weights by p, so that this is w by p, so that here it is p multiplied by w by p, pp cancel out, so it's w. So during test time you just use all your weights as normal, but during training time all your weights are divided by p, where p is the probability with which each of the neurons is turned on, turned off. Now it is possible to use different p for each of the different weights, but that would just mean you have to store double number of values in the memory. So for most of the implementation, people often use a single p throughout the network, or at least use one p for all the neurons in one layer. That way you have only fewer number of things that you have to remember, and also now this p becomes yet another hyperparameter, right? And you want to reduce the number of different hyperparameters that you have. Okay. Now